Welcome to section 1.6. We're going to be talking about functions. Before we can define what a function is, we have to define what a relation is. And a relation is a set of ordered pairs, x, y. And there's different ways to represent this. We can use an equation. So for instance, if we write y equals 3x plus 5, that is a relation between x and y. So one of the ordered pairs in that set, for example, we know there's infinitely many, but if we plug in a x equals 1, y would be 3 plus 5 is 8. All right, so there's one of infinitely many ordered pairs. We also might literally see a set of ordered pairs. We could use set notation, which looks like a profile of someone's face. And we would just gather all our ordered pairs here. So here's an ordered pair, negative 1, 2, for instance, 0, 5, 1, 8. Notice I'm using our function, or excuse me, our relation y equals 3x plus 5 to get these ordered pairs. So it's literally a set of ordered pairs. And again, our set notation are the fancy brackets that look like a face. All right, we can also, we could write it as an equation, a set of ordered pairs. We also know that this is a graph, or it can produce a graph. So a graph would also be a relation. So 3x plus 5, I'll just kind of eyeball it, intercept of 5, slope of 3, super rough sketch. But it's literally a set of ordered pairs, right? A line is a set of ordered pairs. Okay, so all these different ways to represent a relation. I wanted to also take a moment, since we're talking about ordered pairs. You know, we have our x and our y values to get our ordered pairs. We talked about how our x is our independent variable and how our y is our dependent variable. Sometimes with functions in this chapter, we're also going to see we can think of independent as what we're putting into an equation, and the y value is what we're getting out, so an output. All right, so coming over here, this value right here would be our input, what we're putting into our function 3x plus 5. Right? And then the y value could be what we're getting out. All right, so that y value is our output. All right, so just a different way to view the same thing. So when we talk about relations, we talk about all of the possible x values. So all possible x values that our set of ordered pairs can take on. All right, in this set, it looks like there's just 4 x values, or sometimes we're interested in the y values. In this case, there's 4 y values. And then the set of all y values is the range, and the set of all x values is the domain. All right, so when we hear domain, we're going to think of the independent or the x values. When we hear range, we're talking about the dependent or the y values. Okay. All right, so we'll talk more about that in just a second. One nice way to see domain and range is with a mapping. So with a mapping, it's essentially what we're doing here on a graph. We're taking x values and we're mapping them to specific y values. All right, and we see that as an equation sometimes, we see it as a graph. Now we're also going to see it as a mapping where we put all of the x values, now we're calling that domain, in one bubble. So all the x values are our domain. And we show how they map to all the y values. And now we're calling that the range. All right, so for instance, let's say our x values, our domain is 1, 2, 4. And our relation is going to take all of those x values and assign them to a y value. Whoops, let's be more specific. 1 will go there, 2, and 4. All right, so let's say 1 is mapped to 7, and let's say 2 and 4 are both mapped to 9. All right, so again, we created this relation where 1 goes to 7, 2 goes to 9, and 4 goes to 9. Okay, so there you go. All right, so we're defining what a relation is. Now that we have a relation, we can talk about a function. And a function is a relation where each input has exactly one output. So each input has exactly one output. All right, so let's look at what we just came from on this previous page. 1 went to 7. This input or domain, this input went to 9. And this input went to 4. So all of our inputs, all of our x values, did they each have exactly one friend? Yep, 1 goes to 7, 2 is friends with 9, and 4 is friends with 9. All right, so 2 didn't have, 2 friends. Didn't go to 9 and 7, it just went to 9. 4 didn't have 2 friends. It didn't go to 7 and 9, it just went to 9. So this is an example of a function. This relation we just saw is actually a function. All right, let's look at an example of a mapping that's not a function. So we have our domain. I'll do D for domain. And let's say we'll do something simple, 1, 2. Our y values are in our range. Our output is our range. And we'll do 7, 8, 9. And let's say this is our relation in green. Let's say 1 goes to 7, 2 goes to 8, and 2 goes to 9. All right, in this case, our input 2 went 2 different places. It went to 8, and it went to 9. This is not a function. So this example is not a function. And again, the reason is because the input 2 went to 8. The same input went to a different value. So it did not have exactly one output. It had 2 outputs. So it's not a function. All right, and then even as an ordered pair, since the relation is an ordered pair, these would be your associated ordered pairs. And you see we have 1 input, but 2 outputs. Not a function. All right, so let's go back to that original relation, y equals 3x plus 5, that we were looking at the beginning of this section. Is this a function? All right, so this means for every value of x we plug in, do we get a unique y? All right, so let's write that down. So is this a function? What we really want to know is, does each x value we plug in have a unique y? All right, so let's think about this. When we plug in our x, we multiply it by 3, right, 3x. How many numbers do you get when you multiply a number by 3? You get 1, exactly 1. All right, so 3x is one number. We don't multiply something by 3 and get like 37 and 39, right? We just get one number. And then we add 5. How many unique numbers do we get? We still just have one number, right? There's no number where you can add 5 and then you get like 10 and 12. No, you just get one number. All right, so all in all, if we plug in an x, multiply by 3, get one number. Add 5, get one number. And so the y is going to be unique. So it has a unique y value. So we can answer yes to this question. So we could say yes, a function. All right, that's the first part. It is a function. This relation is a function. The next part is, what is the domain and range? All right, what are the x values we can plug in? So normally when this happens, I like to test out negative numbers, 0, and positive numbers. Essentially, I'm asking myself, do I have to exclude anything? Is there anything that I'm not allowed to plug in? All right, so y equals 3x plus 5. Can we plug in negative numbers to y equals 3x plus 5? Absolutely. We can plug in negative 10. We can plug in negative a million. We can plug in negative 1/2. No restrictions. Can we plug in 0? Absolutely. That would just be 5. And what about positive numbers? We can plug in all positive numbers. We can plug in 0.3. We can plug in the square root of 20. We can plug in 1,000. We can plug in any positive number. So our domain is all real numbers. All right, and then as far as the y goes, we can also get any y value. Pick any y value in the world. And then you would plug it in here for y and find a unique x. So domain and range are the same. They're both all real numbers. All right, let's look at another example. We have the absolute value of x. Absolute value is this magical thing that makes everything positive. So for instance, if you forgot how this works, let's just look at x equals 3. Absolute value of 3 is 3. If we were to plug in a negative 3, absolute value of negative 3 is also 3. Absolute value is a distance. Absolute value is always positive. Okay, so is it a function? So whatever we plug in for x, do we get a unique y? And the answer is yes. Yeah, y is always positive. So we can plug in a 3 and the distance from 0 is 3. We can plug in a negative 3, the distance from 0 is positive 3. All right, so that's going to give us unique numbers. Yes, a function. All right, remember absolute value is the distance from 0. And that's a unique quantity. Domain. Are we allowed to plug in anything for x values? Absolutely. Positive numbers, negative numbers, zeros, the whole shebang. And then what about the range? All right, can we get a y equals 0? Yes. Y is allowed to be 0 because the absolute value of 0 is 0. So range is 0. Can y be negative? No, because the absolute value is always positive. Notice over here when we plugged in negative x, we got a positive y. So our range is 0 and all positives. Some people like to use symbols for this. So you can say all y's are greater than or equal to 0. All right. So let's look at this next example. Notice the only thing that's different is that now the absolute value is around the y and not the x. And see what happens now. So let's say x is equal to 3. So we want to know what our y value can be. So absolute value of what is 3? Well, we know absolute value of 3 is 3, but what else? Absolute value of negative 3 is 3. Okay, so what this tells us in this first equation, x equals 3, y equals 3. Down below, we have x equals 3, y equals negative 3. Okay, so same input 3, but two separate outputs. So that means not a function, all right? And then visually, or a mapping, would look something like this. Not a function. All right, so there's a nice example of something that's not a function. Let's continue. Let's look at this table of values. Does this table represent a function? All right, well, I'm noticing right here that our input x, our x values, have 2 1s listed, and 1 goes to 5. If this also went to 5, like if it looked like this instead, that's okay, but we're going to 7. All right, so same input, the number 1 is getting mapped to 2 different outputs, not a function. All right, let's take a look at graphs and consider our graphs for a second. I'm going to draw 2 examples. I'll draw them in red. This is an example of a parabola. This is like a sideways parabola. All right, let's look at the graph on the left. Remember, these are all our inputs. Our x values are our inputs. So let's take an x value and map it to our function. And that's going to tell us what the output is. And there's your output. All right, so here's our x value, and it's associated with one y value, right? And we can do that again. Any x value, we map it to our function, and we get a y. So no matter what x we choose, it's always going to get us to just one y. So exactly one input has exactly one output. That's our definition of function. All right, and let's compare that to this one over here. We'll do the same thing on the graph to the right. Here's an input x, and then look at this case. First, we're mapped here, but we're also mapped up here. Okay, so that one x value has 2 y values. I'll just call them y1 and y2. So this input has 2 outputs. So I don't even have to go farther. We know this is not a function. All right. And in general, when we're looking at graphs, we have a quick way of determining if something's a function or not. Notice the one on the function, if we extend, not a function, if we extend those dotted lines, we can get a vertical line. And we can do the same thing over here, the one on the left. Extend the dotted lines, we get this vertical line. And with the function, the vertical line only intercepts the curve once. Not a function, the vertical line goes through the curve twice. All right, so this leads to our vertical line test down below. A relation is a function if and only if each vertical line intersects the graph no more than once. So if the vertical line intersects the graph no more than once, like here, it's a function. And a relationship is a function if we can draw a vertical line and it only touches our graph once. All right, so a really quick way to see if something is a function or not. Okay, so with that, we've seen lots of examples now. Functions can be represented 4 different ways. We saw an equation. So like y equals 3x plus 5. We just saw the graph of that equation, or a equation. We looked at tables. And then also words. And granted, I just talked about it, but when we were looking at 3x plus 5, I said we can take a number, multiply it by 3, and add 5. Okay, so that is a way we can represent a function. All right, so let's return to graphs now, and we're going to talk about domain and range, and how we can find the domain and range of our functions. All right, so here we have this example, and we want to find the domain and the range. color that in, that dot right here by the -3, 0. Let's color that in too. Okay, so remember, domain is x values. So I'm going to write it in terms of x values. I'm going to do like a 3-part inequality. So moving from left to right. So let's just go kind of trace back all of our x values to our x-axis. All right, so I'm just kind of mirroring or translating the graph up. So if you imagine just smushing our graph vertically so it's on the horizontal line, our whole graph would end up being between -3 and 1. All right, so that tells us our domain. We're going from -3 to 1, right? -3 to 1. And a 3-part inequality, it's going from the smallest number, and they get bigger. So our alligator is going to face to the right, and it keeps getting bigger till 1. So this is saying that -3 is the smallest and 1 is the biggest. All right, let's kind of repeat this process for the range. I'm going to erase. Okay. And then, but we're going to kind of compress it horizontally now over to that vertical axes. So wherever you see a y value, just kind of map it back to the y-axis. All right, so something like this. Every y value we're just bringing back to the y-axis. And so now we're smushing it down to this chunk of numbers here on the y-axis. Okay? All right, so same thing, same notation. The y values look like they start at -4, and the biggest one, it goes up to 0. All right, alligator turns away from the smaller number, and it eats the bigger number. So there's our domain and range. Bonus round, is this little relation a function? I would say yes. And that's because of the vertical line test. So notice if we come in and we draw vertical lines, all of these vertical lines only touch the graph once. So by the vertical line test, it's a function. Okay, let's challenge ourselves. Whoops, soon, sorry. We're still going to find the domain and range. This one's a little bit different. First of all, it's a function by the vertical line test. The domain, this is different because now we have these arrows. And these arrows mean that our function goes on forever. All right, so we can just, if we were to extend this blue line, it would just go up and out forever. These would go up and out forever. Okay, so what's the domain and range? Okay, so first of all, because we're going not straight up, we're not going straight up, right? It's a definite curve, and we're going up and out. Eventually, we're going to hit all of the x values. Eventually, we will hit all of the x values. So this x value all the way over here, like 20, is just going to have a really, 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 really large y value. So our domain, we can just say all real numbers. We can say it goes off to infinity. We can also say it's like this. All of our x values go to positive infinity and negative infinity. If you guys want to do that, that's fine. But let's talk about the range. And then notice, as far as y values go, again, if we play that game and we just take all our y values and map it back to our y-axis, our y values start at -6. And notice there's nothing below -6. All this highlighted region, there's not a y value to be found. So we have to make sure we don't include that in our range because it's not in the range. All right, so we can write this a couple different ways. We can say all the range is all numbers or all reals greater than or equal to 6, or at least 6. Or you can say y is, whoops, I keep saying 6. It's negative 6. All right. Or you can say y is greater than or equal to negative 6. You can say it with symbols too. Okay, so final 2 exercises. And you guys can pause. All of our answers are going to look different. But let's see if we can somehow compare our solutions. So go ahead and pause, and then come back to see how you did. All right, so we're going to sketch the graph of a function whose domain is negative 3 to 5 and whose range is negative 2 to 4. Okay, so I'm going to draw my, kind of box it out first. So negative 3 to 5. And then the range, so those are the x values, and then our range, or y values, is negative 2 to 4. So our whole function has to fit in this window. Sometimes working backwards helps us move the other direction. Okay, so the only thing is that at some point the curve has to touch all 4 sides of this box, and it has to be a function. So think of that vertical line test. Okay, so maybe it looks something like this. All right, there you go. I'll do a solid dot. All right, so it's definitely a function. Our x's are ranging from negative 3 to 5, and the y values are contained within negative 2 and 4. All right, let's do the same thing down below. You guys did the same thing down below, but now it's a relation that is not a function. So same thing, I'm going to do my box. X goes from negative 3 to 5. Y goes to negative 2 to 4. Ooh. And now it's not a function, so that means, think about the vertical line test, has to fail that. So let's say we go something like this, and then like down right there. All right, so our domain, it ranges from negative 3 to 5. The y values go, or range from negative 2 to 4. But now it fails the vertical line test, so that means it's not a function.